students received. Sean's still coming. He's gonna be a little late.
He's not going to come?
He is coming.
He's coming, but just...
Dylan, you need up
He's not
fast,
giving
don't
me
you?
my gift
What?
until
You
next
need
week.
up fast, don't you?
But he didn't make me
Yeah.
act like dinner.
I'm like that when I sleep.
And he ate my chicken.
Okay, so good morning, everyone. I'm supposed to, post the second homework for the slope deflection method for the phase, but I didn't. So for the exam, for the midterm exam, it's on Thursday. Okay. So did you think about this problem? Do you want, like last time, some of you were not here, but we discussed, having a take-home problem. Okay. It would be something close to this. Okay. Would you like to have a take-home problem plus an in-class test? So part of the test will be take-home and part in-class. So I don't want to, make it difficult for you. If you don't like the idea, just no problem. I'm not going to have the take-home part. Did you think about it?
I still don't care either way. It's just me.
And you give us 2 days. You'll give it to us today.
I'll submit it today. Yeah, I'll post it today. You're going to give it back on Thursday. No. Opposed?
No, I'm okay with it as long as we get 2 days.
Yeah.
I got a test Wednesday
Yeah,
and Thursday.
I got 2 tests Thursday and tomorrow.
Okay. So,
I'm not gonna work tonight. I have a test tomorrow.
okay.
I work tomorrow night.
No, thank you. You said that.
No, thank you.
No, thank you.
At least he's polite.
Okay, so the test on Thursday, the entire test will be in class. There is no take-home problem. Okay. Just the exam will be just on beams. Okay. No frames because I didn't assign the homework for the frames yet. Okay. So just beams. So that's very straightforward. Okay. And how many problems will be on the test? 4? No.
3.
3. Okay? So that you have enough time. So don't worry about time. Okay? There's going to be 3 problems on the test. Okay? There will be plenty of time. You have 75 minutes, so you have 25 minutes per problem. Okay? So I guess it's going to be like good, decent timing for the test. Okay? Any question about the test?
Can we expect beams on the next test?
No.
I mean, not beams, I'm sorry, frames?
Phase on the next test, yes. So beams on this test, maybe phase and something else on the next test. Okay?
So basically, do our homework over.
Somehow,
Your homework, try to solve as many problems at the back
With
of the
the
chapter.
beams.
Yeah,
Okay.
beams. Okay? You can expect anything for beams, modified, you can use the modified slope deflection equation, settlements of supports, movement of supports, okay? Beams where you can have a delta, the displacement, okay? So anything as long as it's a beam can be on the test, okay?
Will you give us that back page of our book, that sheet?
If you need something from there, you will have it, don't worry.
Okay.
Yes.
How about if you do give that to us as a tech home, like homework, I guess? Could it like replace homework 1 or be like a bonus?
This
If I
one?
didn't do homework 1. Yeah.
Maybe by the end of the semester. Let's see how you're doing. Well, if you're doing well, okay? And I'm really happy with your performance in the, steam bridge competition. I really care a lot about the steam bridge competition because this is going to be, presenting ASU in the competition. So I really want you to do a good job. If you don't do a good job in the steam bridge competition, okay, I'm not going to help you, okay? If you do a good job there, I'm willing to help each and every one of you, okay? So take it serious. The steam bridge competition frankly, okay, I don't think many of you are taking it seriously. Okay? You don't think a lot about the dimensions. Many of you had, things that were not compatible with the the required dimensions. So please take it seriously. I really care about this a lot. Not only me, by the way. Okay, Mr. Stewart, Dr. Wang, okay, the lead, everyone, because this represents ASU. Okay, so take it seriously. Okay. So finally, we finished the slope deflection method. Okay, we're gonna start the new method. Okay, so in this semester, we're covering two methods of solving indeterminate structures. Okay, we finished the first one, the slope deflection method, and now we'll start the second method called the matrix structural analysis for beams. Okay. The matrix structural analysis, as we saw for the slope deflection method, we covered this for beams and frames. So the slope deflection method can only be used for beams or frames. While the matrix structural analysis, it's considered like an extension, okay, or a modification, okay, for the slope deflection method, but it can be applied. This concept of matrix structural analysis can be applied for beams, frames, and trusses, okay. So we're going to start by its application on beams, okay, and then we're going to apply it to trusses, and then finally frames is just a combination of beams and trusses, okay. So let's start today with the matrix structure analysis for beams. This is chapter 15, okay. In the book, it starts with trusses first, but I prefer starting with beams, okay. So this is chapter 15 in your textbook, okay? So this is, it's called matrix structure analysis, okay? Sometimes we call it the stiffness method. Or sometimes you can call it the finite element method. Frankly speaking, the finite element method is more extensive than what we're going to cover here. So the finite element method is more general and involves more steps. It starts from very basic equations and then reaches what we're going to reach here, okay? So, for example, finite element methods, just to know what's finite element method, what we're doing here is just a small part of the finite element method. What we're going to do here, the matrix structure analysis here, is just a small part of the finite element method. The finite element method mainly is a numerical method of solving differential equations or partial differential equations. Whatever this partial differential equation is, okay, this is the purpose of finite element methods, okay? This partial differential equations can be a mechanics equation, okay, or equilibrium equation. So for example, okay, what we have here, okay, we can represent the equilibrium, okay, of objects or bodies, okay? You represent, how do you represent equilibriums of objects? You say sigma fx is equal to 0, right? This is how you represent equilibrium. Sigma fy equal to 0 and sigma moment equal to 0, right? This is how you represent equilibrium. But this is like the basic way of presenting equilibrium. This is for discrete elements, okay, for just 1D elements, okay? While for representing this for small elements, this becomes a differential equation, or actually a partial differential equation. So instead of having like this type of equations, if you have an object that looks like this, you can apply the equilibrium on a small part here. Let's say this small part, okay, it looks like this. Small infinitesimal element here, okay? And you actually realize that this equation becomes a partial differential equation. The differentiation of sigma xy by the y and so on, some other term, sigma xx by dx, okay, is equal to 0. This is what you end up applying this equation equilibrium for a small infinitesimal element here. It's a differential equation, partial differential equation. So actually the finite element method just solves this partial differential equation. So you start from a very basic partial differential equation, you apply the finite element method, you're going to reach what we're going to be doing here. Okay? So the finite element method is a very, very general method. Okay? It can be used to solve partial differential equations like this one, or for mechanics or people in mechanical engineering. You can use it to solve like the heat equation. Okay? How the temperature profile in an object like this, a 3D object. Okay? So finite element method can be used for a variety of equations, whether it's displacement, heat, temperature, diffusion, concentration, many problems that can be used, or you can use the finite element method. Okay, so we're not, mainly doing finite element method here. Okay, we're not going to be doing finite element method. Okay, it's just a small part of the finite element method that we're going to be doing here. Okay, just the last step of the finite element method. Okay, this is called the matrix structure analysis. So now, why it's called the finite element method? Okay, so in this method, the structure is divided into discrete members, or we can name it finite elements. That's why it's called the finite element method. Finite elements connected together at their ends by nodes. So we break our problem, okay, our structure, into elements, okay, and those elements are connected by nodes, okay. The points of connections are nodes, okay. As we see here, we can name this method matrix structure analysis, or stiffness method, or finite element. So there is a reason behind each of those names. We said the finite element method, it's named finite element because you break your structure or your body, your object, okay, into small finite elements. That's why it's called finite element method. Okay? This is usually like if you have an object, a continuous object like this, so you break it into a set of elements. Okay? So this is an element, and then they are connected by nodes here. Okay? So that's why it's called finite element method. Okay? And then matrix structure analysis, why it's named or can be named matrix structure analysis, because at the end, what we're going to be solving is a matrix. We're going to have a matrix equation, okay, that we're going to be solving. Or stiffness methods. So this method is based on the concept of stiffness. So what's meant by stiffness? So now, let's say you have a spring here, okay? And there is a force here, P, applied on this spring. What will happen to this spring? It will get compressed. So it will just get compressed by some distance, U. Okay? How much is U? U depends on what? The stiffness constant, the spring constant, and the load P. As P increases, U increases, right? So U, okay, increases as P increases, right? and the stiffness here of this spring, which is represented by the term K, the stiffness. Okay? What does this mean? It means like you can have a spring made out of steel, okay? Or it can be made out of plastic, right? Definitely the steel one would be harder. You need large force to, compress it, right? So K depends on how stiff is your, spring here. So the relationship here becomes P equals KU. Okay? K represents the stiffness here. So K is the stiffness of the spring. So now, what does K represent? If I want to give a definition for K, K, or the stiffness, if you want to define it, how would you define it? From this equation, just give me a definition for K from this equation. K is the force required to give a unit displacement, right? If U is 1, then K is the force, right? So this is the definition of the stiffness, okay? So K, okay, is the force required to give a unit displacement. Okay, so that's the definition of K. You have to put this in mind. Always just remember, K is what? It's the displacement, or sorry, the force due to a unit displacement. Okay, that's the definition of the stiffness of something. Okay. Is the stiffness always like related? You have to have a spring to have a stiffness? No, I can have an element, a member that is like this. Applying also a force P here will give you some compression U. It doesn't have to be a spring, right? An element, any element in life, any material, if you put a force on it, it's going to get deformed, right? So here again there is stiffness, okay? K is what? K is the force required to give a unit displacement in that element. Okay? And if you, like, for example, use Hooke's law, E is sigma divided by epsilon. So E, the modulus of elasticity, sigma is the stress, which is P divided by the area of that element. The strain is the deformation, which is U divided by the length of that element. So here, to put this equation in a form that is similar to this, we're going to have here P equals to EA divided by L multiplied by U. So what does this mean? It means that K, the stiffness of this element, is EA divided by L. This is the force required for a unit displacement. Okay? So this is the definition, okay, of the stiffness, okay? The force required to give you a unit displacement. So now let's extend this concept now a little bit, okay? Let's say you have an element or a spring. We just realized now that they are similar to each other, and they are connected here at this node, okay? So I have a spring or an element here, and a spring or an element here, okay? And now I apply a force P at this node. What will happen? This point is going to move here, let's say. U will move up the distance U. I would like to find the relationship between P and U. Okay? I would like to find the relationship between P and U. So now I have two springs. Let's say this is K1, okay, and this is K2. What is the relationship between P and U now? if you only had this spring, let me erase this. If you only had this spring, okay, you apply force P. What's the relationship now? P is equal to K1 times U, right? If you only had the lower one, the lower spring here, with this P, P is going to be equal to K2 times U, right? But now if you have both springs together, okay, what will happen? You will need a larger force, right, to have the same displacement, right? Because you need to push this spring and you need to push this spring, both, right? So this is, let's name this P1 and P2, okay? So if I want to have the same displacement, I will need a larger force, right? So now adding, if I have both together, so this one plus this one, so this is B1, this is B2, K1, K2, okay? This is U here. So you're going to have B1 plus B2 is equal to K1U plus K2U to have the same displacement. So you have K1 plus K2U. So I'm going to name those P1 plus P2 is equal to P. So if you apply force P here, this force P is going to get, two parts. P1 is to compress this one, and P2 to compress it, or elongate this one, right? And the relationship between the total force now, P and U, is given like this. The total force P and the displacement. The displacement here is the same displacement as here, right? But the force here is not the same force as this one, and they are different from this one. Actually, P1 plus P2 is P, right? So P, the relationship between the total force and the displacement is, you have to sum the stiffness coefficients together, K1 plus K2. So this is a very, very important relation that we just reached now. If you have a node that is shared between two members, when you write the stiffness equation, this is called the stiffness equation. P equal Ku is called the stiffness equation. Here, this is again the stiffness equation, but what you have to do is the stiffness coefficient here, you have to add the stiffness of all the elements that are connected to that node. Okay? Now, does it have to be two elements? No. Let's see another example here. Let's say this is a very rigid bar, okay, so that it doesn't deform. You have a spring here, a spring or an element here, spring or an element here, and the stiffnesses of those are K1, K2, K3. You apply a force here, P, so this moves down a distance U. What's the relationship between P and U? P is Ku. What's the stiffness here now? K1 plus K2 plus K3. You just have to add the stiffness of all the elements that are connected together. Okay? This is simply what we want to reach now. Okay? We have this stiffness equation. We just want to formulate this stiffness element. Okay? If it's just one element, then it's K. If it's two, then K1 plus K2. If you have three connected at the same node, then K1 plus K2 plus K3. Okay? It's that simple. Now, what we did is we wrote this stiffness equation, okay, when we had a displacement like this. So now the displacement was a linear displacement, okay, at the node, a vertical displacement or an axial displacement. Let's be more precise here. It's an axial displacement. It's in the direction of the element, right? Now, can I write the stiffness equation, but for different type of displacements? Yes, that's what we want to do now, okay? So let's say we have an element that looks like this, a beam element. We want to start with a beam, okay? So we have a beam element, okay? It has a length of L and E is the modulus of elasticity of the material of which this element is made of. I is the moment of inertia of that element, okay? So EI is the multiplication of elastic modulus multiplied by the moment of inertia, okay? And we have this element. It has a start point and an end point, okay? We're going to name those N and F, okay? So for the shown element, this is beam element. So as you see here, the word element, okay? This is why we call it finite element. You have this element, okay? For the shown beam element, NF, okay? We're going to use N, okay? Is used for the near end of the member and F for the far end of the member. So what are the nodes here? We said the finite element method, you have elements and there are nodes. What are the nodes here? What are the nodes that we have on this element? N and F. Okay? The stiffness coefficients are the values of, what's the definition of the stiffness coefficient? K. The value of the force, right, required to generate a unit displacement at the nodes. Okay, this is very important, at the nodes. Okay, so now, what are the allowable displacement that this element can have? You know this. We did this in the slope deflection equation. Each of those points can have a rotation, right, and a deflection, right, and generally, we're going to have an axial displacement too. So each of those nodes can have a rotation like this. It can rotate. It can move up or down. It can move to the left or to the right. Those are the kinematic degrees of freedom for this node, just for the node, okay? Not for the entire element, just for the node, okay? So let me write this here. So the question is, if I ask you what are the allowable displacements at each node, there are simply, or in a general case, each node has 3 kinematic degrees of freedom. Which are ux is an axial displacement in the direction of the member, uy is a lateral displacement, and the theta, which is a rotation. So each node here can have a, let's draw those in different colors so that you can, so ux, okay, the vertical one here, this point can move up or down. Uy, and let's draw this in green, can have a theta. So each node can move vertically, horizontally, or rotate, okay? The element can rotate at this point. So those are the 3 degrees of freedom that we have, okay, at each node, okay? Now, to be consistent with what we did in the slope deflection method, we're going to neglect the axial displacement, okay? So for beams, we can neglect the effect of the axial deformation. So therefore, for a beam element at each node, we only have 2 degrees of freedom, which are uy, the lateral displacement, or we can name it delta, okay, and theta, a delta and a theta at each node, okay? So now we want to find the stiffness coefficients. So now let's say, again, it's the same beam element. The beam element is always the same. It's an element with a node N at the start and node F at the end. It has a length L. L can be any value. And it has an EI value. Okay? Now, to find the stiffness coefficients, we said what's K? K is the force required or generated due to a unit displacement, right? So now, let's say, if you have a unit vertical displacement at point N, or node N, so this is a unit vertical displacement at node N. Everything else is 0. So the rotation is 0. We already said we're going to neglect the horizontal displacement. There is no horizontal displacement here or here. This point F is not moving, okay? I'm just putting a unit displacement at node N. I put the unit displacement at node N. The generated force is K, right? K is the force due to a unit displacement, right? That's the definition of K. So now, if I have the unit displacement here, once you put the unit displacement here, there will be this element to be in equilibrium. There might be a moment here. Let's name this Mn, the moment at point N. There can be a vertical force here. Let's name this Fn in the y direction, the force at node N in the y direction. There can be a moment here. What would you call this? Mf, right? And there would be a force here, the force at point F in the y direction, okay? So now, the problem, as you see, it's different. You apply a unit displacement, there would be 4 forces generated. So the stiffness coefficient, okay, it's not just one stiffness coefficient. It's now many stiffness coefficients. Okay? You apply a force. Okay? There is a set of 4 displacements or 4 forces that would be generated due to a unit displacement, not just one. Like here, in the problem that we started with, you apply a unit displacement, there is a force here, just one force. Okay? But now, for this, you apply a unit displacement here. You have those forces generated. Okay? 4 forces generated due to a unit displacement. So now, those are the stiffness coefficients, not just one stiffness, 4 stiffness coefficients. How much are those values now? Mn, Fny, Mf, and Ffy that are needed or would be generated due to a unit displacement here. Can you answer this question? How can we answer this question? We need to find Mn, Fny, Ffy, Mf due to a unit displacement at point N. Equations of equilibrium? There are 4 forces here. So applying the equations of equilibrium might help, but they're not going to be sufficient. What? How can you find those forces?
Here, I'm sorry, will you not use those again?
No, the slope deflection equations. Okay? The slope deflection equations would give you the magnitude of those forces. So now, you're an expert in the slope deflection equation, right? We're going to have a test on Thursday. You should be an expert now. So applying the slope or from the slope deflection equations here, what does the slope deflection equation gives you? If you have an element like this, how much is Mn? How much is Mn? 4EI divided by L, right? Multiplied by theta n. How much is theta n? 0, right? Plus 2EI divided by L. So let me write this. 4EI divided by L, theta n. And theta n is 0. Plus 2EI divided by L multiplied by theta f. How much is theta f? 0. Why? Because I'm not putting any displacements here. The only displacement is this one. Right? Minus 6EI divided by L squared delta. How much is delta? 1. Plus the fixed end moment. How much is the fixed end moment? 0. So actually Mn, okay, is negative 6EI divided by L squared. That's the stiffness coefficient. That's the moment at point N due to a unit displacement at point M, which is the definition of a stiffness coefficient, right? The definition of the stiffness again. What's it? The force due to a unit displacement. This is the force. This is the moment due to a unit displacement. Negative 6EI divided by L squared. But now, this is a very important point, okay? We want to use a different sign rule, or different sign rule here. So, it's going to be different from what we used for the slope deflection method, unfortunately, okay? So you have to realize that the sign rule is different, okay? Now, this unit displacement was upwards, okay? So if it's upward like this, what happened to the member? It had a clockwise rotation, right? So if we have a clockwise rotation like this, okay? So the moment is going to be negative 6EI divided by L squared. What does the negative mean? What's this? The negative means, this is a slope deflection equation, right? I put this 1 as positive because this rotated in a clockwise direction. This is negative. That means that this moment is counterclockwise. Okay? So the negative here means that it's counterclockwise. So you put a vertical and upward vertical displacement at n. This moment is a counterclockwise. Okay? Now, MF. What about MF? 4EI divided by L theta F, which is 0, plus 2EI divided by L. 4EI divided by L theta F, which is 0, plus 2EI divided by L theta N, which is 0 as well, minus 6EI divided by L square delta, which is 1, okay? And the moment which is 0, and the fixed end moment which is 0. So MF is negative 6EI divided by L squared. So this is the negative here, means that this is 6EI divided by L squared, and the negative means it's counterclockwise. Here this is negative, or I can say it's 6EI divided by L squared, and the negative means it's counterclockwise as well. Okay? Now, as you see, we know the magnitude of MN, MF. What about FNY and FFY? Yes?
Mine is delta 1 on the side, the far side.
Y is delta?
Yeah, y is delta 1 on the far side. You're not displacing on that side, you said you're carrying 0.
Yes, but the element rotated. You remember the slope deflection method?
Yeah.
We said if there is a rotation in the member, there is moments for both ends, right? So now, I would like to find FNY and FFY. How can I do this? Is there a slope deflection equation that gives you FFY and FNY? No. How can you get them now? No. Don't break the beam. Taylor, what did you say? Equations of equilibrium. Okay? Just apply the equations of equilibrium. Okay? From equilibrium, taking the summation of the moments about point n is equal to 0. What do we have here? This moment was 6EI divided by L squared. This moment was 6EI divided by L squared in the directions that I drew here. Okay? If you take moment here, you're going to have 6EI divided by L squared plus 6EI divided by L squared minus FFY multiplied by L equal to 0. Right? So this is what I'm going to write here. 6EI divided by L squared plus 6EI divided by L squared minus FFY times the distance L is equal to 0. So FFY is 12EI divided by L squared, not L squared, divided by L cubed, right? 6 and 6, that's 12. Here you have L squared, and then you're going to move this to the right side, right-hand side of the equation, and then you divide by L, so this becomes L cubed. So FFY is 12EI divided by L cubed. In this direction, what's this direction? Downwards, okay? So this is downwards. So those moments, this is counterclockwise, this is counterclockwise, FFY is downwards, okay? So now what we did, again, find the stiffness coefficients here, okay, we applied a unit displacement upwards at point N. Okay? Now continuing the equilibrium equation, continuing using the equilibrium equation, equilibrium equations, we have sigma Fy equal to 0. What does this mean? Fny is 12EI divided by L cubed, and it's upwards. Right? This is the free body diagram here. Those two forces has to be equal and opposite, right? Sigma Fy is equal to 0. You know this one, it's 12EI divided by L cubed. This one has to be 12EI divided by L cubed, but if this one is going downwards, this one is going upwards. Right? What are those four forces? I'm just going to put them in red rectangles. What are those by definition? The stiffness coefficient. Those are the forces due to a unit displacement. Right? Those are the stiffness coefficients. The values enclosed in red are the stiffness coefficients, or by definition, those are the forces generated due to a unit displacement. Okay? To give some sign rule here, we're going to write a new sign rule that we would use with our stiffness coefficients, okay, and our stiffness method. This sign rule is completely different from what we used with the slope deflection. Although we use the slope deflection equation to find those values, but we're going to have a different sign rule, okay? What's that sign rule, okay? So the sign rule here that we're going to use for any moment or rotation, okay? For any moment or rotation, if they are counterclockwise, they are positive. What's this? This is the opposite of the slope deflection equation. The slope deflection moments and rotations were positive if they were clockwise. Now it's the opposite, okay? If they are counterclockwise, they are positive, okay? Fy and delta. For the slope deflection method, we had a rule for delta. If the delta rotates the member in a clockwise direction, then it's positive, right? If it rotates counterclockwise, then it's negative. Now, for Fy and delta, we're going to have a different sign rule. If they are upwards, they are positive, okay? If they are downwards, then they are negative, okay? So upwards are positive. So you have to realize that this is a completely different sign rule. So now, when I apply this unit displacement, is this unit displacement positive or negative? Positive, it's upwards, okay? Not because the member rotated in a clockwise direction. No, it's upwards, so it's positive. This moment, 6EI divided by L squared, it was counterclockwise, so is it positive or negative? Counterclockwise, positive. This moment, it's counterclockwise, so it's positive. This force, FFY, it's downwards, so it should be negative. This one is upwards, so this one is positive. Okay? So this is the sign for those forces that we found now. Okay? Now, what are those? Those are the stiffness coefficients due to a unit displacement here. Okay? What if I want to find the stiffness coefficients due to a unit displacement here? This is point N, point F. Now I put a unit displacement here. Only a unit displacement at point F. This is one, a unit vertical displacement at point F. If you put a unit displacement at point F, there will be forces generated here, right? MF and MN and FFY, FNY. How much are those? So now, applying a unit and upwards unit displacement at F. How can I find those moments? MF, MN, FFY, FNY. The same as we did when we had the unit displacement at the other end. So M, for example here, MN, it's 4EI divided by L theta N, which is 0, plus 2EI divided by L theta F, which is 0. This displacement, I'm using the slope deflection equation now. This displacement, is it positive or negative?
Oh, you said slope deflection.
I'm using the slope deflection equation, so this is negative. So you have negative 6EI divided by L squared delta, which is negative 1. Okay? So MN is 6EI divided by L squared. It's positive. What does positive mean in the slope deflection equation? It's clockwise. So it's negative for the stiffness method. Okay? Since it's clockwise, so it's negative in the stiffness method. Okay? So this is negative 6EI divided by L squared using the stiffness sign rule. Similarly, you do the same, you can find MF, okay? It becomes negative 6EI divided by L squared, and then the equilibrium equations, you find F and Y, you will find, so here similarly, F and Y is going to be negative 12EI divided by L cubed, and Fy is going to be 12EI divided by L cubed. What are those? Those are named the stiffness coefficients as well. Those are the forces due to a unit displacement, but it's a different unit displacement. Instead of point N, it's at point F, right? Now, are we done with those stiffness coefficients? No. I still have two other displacements that are allowed to happen, right? You agree with this or not? We said for a beam element, each node can have, we said we're going to neglect the axial displacement, but each node can have a delta and a theta. What I did now is I just put a delta at the near end equal to 1 and the delta at the far end equal to 1 and I find the forces, right? There are still theta at the near end can happen and a theta at the far end can happen. If there is a theta at the near end, what's the stiffness coefficient? If there is a unit displacement or a unit rotation at the near end, how much is the forces? Okay? So now, applying a unit rotation at point N. We're going to apply this unit rotation in a positive direction. What does positive mean? Counterclockwise, according to the sine rule of the stiffness method. So this is positive. But according to the slope deflection method, this is negative. Okay? So we have this element now. Again, this is point N. This is point F. The member length is L. It's EI. And now I'm putting a unit displacement in a counterclockwise direction at point N. So here, there is a theta N that is equal to 1. It's counterclockwise. If you have this theta N here, what will happen? You're going to have a moment Mn, a moment Mf, right? And the force Fny, and the force here, Ffy. How much are those? Applying the slope deflection equations. Since you're applying the slope deflection equations, you have to revert to the sine rule of the slope deflection equations. Mn is how much? 4 EI divided by L, theta N, right? How much is theta N? Negative 1. It's positive 1 using the sine rule of the stiffness method. But it's negative 1 using the slope deflection sine rule. Okay? Negative 1. Plus 2EI divided by L, theta F. How much is theta F? 0. Minus 6EI divided by L squared. Delta. How much is delta? 0. There is no delta here. Okay? I just have, the only thing that I have is theta M. That means that Mn is negative 4EI divided by L. Right? What does the negative mean here? It's counterclockwise. Right? Negative in the slope deflection equation means it's counterclockwise. So therefore, Mn, so this is using slope deflection sign, it becomes positive 4EI divided by L using stiffness sign rule. They are opposite in signs. The slope deflection method and the stiffness method, they are opposite in signs. Okay? So this is Mn. Similarly, you do the same, okay, to find the rest of the forces. Definitely you can do it. I'm not going to do it one by one here. You can find Mf. It's going to be 2EI divided by L. And from equilibrium, you find the two vertical forces, F and Y, is going to be 6EI divided by L squared, and FFY is going to be negative 6EI divided by L squared. What are those values? Enclosed in red rectangle. The stiffness coefficients. The forces due to a unit displacement. Right? Due to a unit rotation. Okay? Now, the only thing left. What's the only thing left here? Now, a theta at the far end. Okay? So, applying a theta at the far end, a unit rotation at the far end F, we're going to find that Mn is 2EI divided by L, and Mf is 4EI divided by L, and Fny 6EI divided by L squared, and Fy is negative 6EI divided by L squared. Those are the stiffness coefficients as well. Okay? How many stiffness coefficients did we wrote right now? 16. We had 4 allowed displacements. A vertical displacement at the rotation and the near end, and the vertical displacement and the rotation at the far end, right? 4 displacements. When you apply each of those displacements, you can have 4 forces, right? A moment and the vertical force at the near end, and the moment and the vertical force at the far end, right? So each time you apply displacement or rotation, you have 4 forces. You have 4 different displacement and rotations. So 4 multiplied by 4, you have 16 different coefficients. Okay? Now, just go back up here. You remember this? P equal KU. Okay? P equal KU. So now, if you have a unit displacement, U is 1, P is equal to K, right? But if you have any other displacement other than 1, if it's 2, P becomes K times 2, right? So now, applying this to what we have here, if the unit displacement here, or the displacement was not units, so those moments would be multiplied by the displacement, right? If the displacement was not 1. Now, let's say what we did is we broke down the allowed displacement into 4 different cases. Just the displacement here, just a displacement here, just a rotation here, and then just a rotation here. What if you had the 4 different displacements combined together? How much would the forces be at the ends? You just add those stiffness coefficients, right? So this is what we're going to do now. Applying the 4 displacements at once, how much would Fny be? Let's go here. Fny. How much is Fny due to a unit displacement at n? It's 12EI divided by L cubed, right? It's upward, so it's positive. So 12 EI divided by L cubed due to a delta, a unit displacement at n. If it's not a unit displacement, so you have to multiply by the value of the displacement at n, right? So 12 EI, we're going to have here 12. Let me write this. This is the stiffness coefficient, 12 EI divided by L cubed multiplied by the displacement, delta n. Whatever delta n it would be, you would just multiply it by this value. What if you had a theta n due to a theta n? This is theta n. When we had a unit rotation at n, f n y was 6 EI divided by L squared, right? So here, if I have a theta n, I have to multiply it by 6 EI divided by L squared. What if I have a delta f? A delta f. Here I have unit, okay? Fny was negative 12 EI divided by L cubed. So I just use this. I'm just combining the four equation or the four values. Negative 12 EI divided by L cubed multiplied by delta f. And then for the theta f, this is a theta f, 6 EI divided by L squared, positive. So here we have 6 EI divided by L squared multiplied by theta f. So if I have those four displacements at once, this would be Fny. Right? You agree with this? And then I'm going to do the same now for Mn. I'm just going to combine the values from the values that I got before. 6 EI divided by L squared multiplied by delta n plus 4 EI divided by L multiplied by theta n minus 6 EI divided by L squared delta f plus 2 EI divided by L theta f. Okay? And the same, Fy due to the four displacements. What are the four displacements? A delta n, a theta n, a delta f, a theta f. Those are the displacements here. Okay? Due to a delta n, you can find this. Okay? From case 1, it was negative 12 EI divided by L cubed. A theta n, it was negative 6 EI divided by L squared. A delta f, this was 12 EI divided by L cubed. A theta f, this was negative 6 EI divided by L squared. And then similarly, if I want to find MF, due to the four displacements, delta n, delta f, and theta f, those would be 6 EI divided by L squared, 2 EI divided by L, negative 6 EI divided by L squared, and 4 EI divided by L. Okay? What are those red values? Those are the stiffness coefficients that we just calculated. Okay? We're just combining all of them together in one equation. Okay? Is it clear for everyone? Okay? Now, as you see, we have four equations now. Okay? The stiffness equation. Do you remember writing the stiffness equation? The stiffness equation looked like what? P equal Ku. The force is equal to K multiplied by the displacement. The stiffness factor, or the stiffness coefficient, multiplied by U, right? I can write those 4 equations as just one single equation, P equal KU. But now this equation is a matrix form, okay? So now, writing this equation in a matrix form, we would have P. What's P? This forces. The forces P. How much is in a matrix form? This is P. This is 4, a vector that is 4 by 1, right? So P here is a vector that is 4 by 1 equal to K multiplied by the displacement. How many displacements do we have? How many displacements? Delta n, theta n, delta f, theta f, 4. So this is a vector. This is 4 by 1. And K is a matrix that have all those 16 coefficients. It's a 4 by 4 matrix. So again, those 4 equations, I can just write them as the equation that we wrote before, P equal KU. But now, instead of just being one equation, P equal KU, it's a set of equations, okay, that I can just write it in a matrix form, B equal KU. So this is a one equation that can be expanded into 4 equations. P, so now, P, which is 4 by 1, I'm going to name this the load vector, or the force vector, okay? And this have Fny, Mn, Ffy, and Mf, the 4 forces, okay? U, which is 4 by 1, I'm going to name this the displacement vector, which has the 4 displacements, delta n, theta n, delta f, theta f. And K, I don't have space here, which is 4 by 4. This is a matrix, not a vector, okay? We're going to name this the member. This is the member. We just had a member, NF, right? This is not a structure. This is just a member, okay? So this is called the member stiffness matrix. It's not a coefficient. It's a matrix of coefficients, okay? And how does this look like? It's a 4 by 4 matrix. Just putting those factors now, it's 12 EI divided by L cubed, 6 EI divided by L squared, 6 EI divided by L squared, negative 12 EI divided by L cubed, negative 12 EI divided by L cubed, 6 EI divided by L squared, 6 EI divided by L squared, 4 EI divided by L, negative 6 EI divided by L squared, negative 6 EI divided by L squared, 2 EI divided by L, 2 EI divided by L, and this is 12 EI divided by L cubed, and this is negative 6 EI divided by L squared, negative 6 EI divided by L squared, and here we have 4 EI divided by L. This is the member stiffness matrix for a beam element, okay? What does this mean? What does this stiffness matrix mean? K, what's K? It's the force due to a unit displacement, right? Why do we have 16 elements here? Because those numbers relate different forces to different displacements. 4 different forces to 4 different displacements, right? So you have to understand what each element here represents. The row here, we had delta n, theta n, delta f, theta f. And for the column, this represented fny, mn, ffy, mf. So what does this mean? When I ask you what does this number mean, it's the force Fny due to a unit displacement at the near end. What does this number mean? It's Fny due to a unit rotation at point N. What does this number mean? It's Mn due to a unit displacement at F. Okay? What does this number mean? It's Mf, the moment at point F, due to a theta F, a unit displacement at F. How's this organized? You have to make sure you understand what's written here. Okay? So again, what we did today is just P equal Ku. But we just started from P equal Ku as just a single equation to a set of 4x4 equations in a matrix form for a beam element. Okay? Any question here? Okay. So we're going to continue on this next time, on next Tuesday.
I just wanted you to know, I thought I did that by putting this loading rail, instead of just doing blocks on each segment, I did it all the way across. I'm not,
Okay. No, I didn't subtract points for this. Okay?
I just wanted you to know that
Yeah,
I
but-
did think about that, but I
Yeah,
did it
but-
all the way.
Okay. We said like we want to have like a double element. So you want to increase the moment of inertia, right? Like you have I, okay? To increase I, we said the deflection delta is like WL 4 divided by EI, something like this, okay? So you want to maximize I to decrease delta. So you have a limitation. This is limited to 4 inches or 6 inches, right?
Right.
So if you use 4, 6, that's fine. But we want to have this longer and longer, or be have a larger depth so that I increases. Okay.
Right.
So if you do this, if you just put a small element here, you didn't increase the distance.
Okay.
You want this to be as large as possible. So you want to use 4 or 6 plus another 4 or 6. Okay. And then you put the highest weight here and here, and the elements here, you use very light elements.
Okay.
Because what's in the middle here, this comes at the neutral axis, so it's not going to give you or increase your moment of inertia because it's near the neutral axis. But you want those to be as large as possible and as far as possible from the neutral
From
axis.
apart. Okay.
From the neutral axis. So just putting a small element here, it's not going to help. We want to put 2 elements. That is, 4 inches or 6 inches. You need to use the entire,
Right.
limited, or the entire limit of the depth, okay? To increase the limit of, or the depth of the entire element, putting those 2 elements together.
Okay.
If I put 4, 6, and then just put a small element here, I didn't utilize this.
Yeah.
And in the end, I'm still going to have to do the connection between the elements.
Right. Okay.
Okay?
That makes more sense. Okay.
So when you do this now, try to use very light elements here, right in the middle,
Yeah,
as small as possible.
Leave
And
them
then
hollow here, and then solid along the
maybe,
bottom
or
and the top.
yeah, the thickness, maybe use a very, very small thickness that it's hollow